Okay, so today I'm going to take any questions you have on the quiz. I didn't grade them yet though, so I can't answer questions about like, what if I did this? Or how many points would you take off for that? So questions about what the answers to the quiz questions are, I'm happy to take those if you weren't sure how to approach the questions. We're going to go over the parametric derivative, which we touched on last Friday. We're going to very quickly talk about polar equations and their derivatives. That's actually really easy, but it looks kind of strange. And then we're going to preview section 3.7. So kind of a lot of miscellaneous topics today. I have, for day 56, some homework assignments for you for those polar equations, the parametric derivatives, and some numerically based derivatives using a table. And then you've got 5 questions to do for the implicit differentiation topic, which we'll do at the end. Okay, so let me start with any questions you guys have about the quiz. You want to take a quick look at it? Any of these give you any trouble?
For number one, were you supposed to put it in terms of sine and cosine before you started?
Yeah, let me show you what I had in mind for number one, and then you'll get the same answer no matter how you approach it, assuming you do it correctly. But number one is actually really easy if you simplify first. And I know gave you that hint. So what I would do here for number one is I'm going to rewrite this as tangent times 1 over secant. Okay? And then I'm going to take the reciprocal of secant, which is cosine. Okay? And then I'm going to go to that's an arrow. I'm going to go to all sines of cosine, so sine x divided by cosine x times cosine x. And then the cosines cancel. And you just get sine x, and that's before you do any derivatives, right? So if you use trig identities, and these aren't the complicated trig identities, these are just basic ones that we covered in the review, you just get f of x equals sine x, okay? Which means that the derivative is cosine x. And that's it. That make sense?
Yeah. I just realized I did it wrong. Oh my god.
It's okay. All right, that's why we do revisions. That's why, you guys have lots of homework assignments where you get full credit for just completing it. So, you can make mistakes in here. It's okay. Other questions on the quiz?
Can you go over number 5?
Number 5, yeah, I can do that. So the goal with number 5 was basically to assess the trig functions. So there's no chain rule in that one. So I'm assessing your ability to do the trig functions and to find the tangent line, which you would need to be able to plug in pi over 6 into trig functions. So let's take the derivative first. So we're going to do sine times the derivative of cosine, which is negative sine, plus cosine times the derivative of sine, which is cosine. Okay? And simplifying, this is negative sine squared x plus cosine squared x. And that's the derivative f prime x. Okay? Now, anytime we're going to do these ones with the equation of the tangent line, we need x, y, and the derivative. So let me take this opportunity to show you a different notation for the equation of a tangent line. So I've been giving you guys just basic point slope form, okay? Let's assume that we call x1 a, like we've done in previous equations. So that means that y1 would be f of a, right? You plug in a into the f of x, you get f of a. And then the derivative m would be f prime of a, right? So the derivative at that point, which means that I can rewrite this equation as y minus f of a equals f prime a times x minus a, okay? So it's literally the same thing, but it's just using function notation instead of, the algebra 1 type thing that you would have seen previously. So let's grab this. I'm going to put it over here. And we know x1 is pi over 6. All right. Let's find y1, or f of a. So to do that, to find our y value, we're going to have to plug in pi over 6 into this thing. So I'll do that over here. So it gets a little messy because, I'm trying to put everything on one screen so you can see it all. So f of pi over 6 is sine pi over 6 times cosine pi over 6. Sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. Multiply them together, you get root 3 over 4. Okay? So f of pi over 6 is root 3 over 4. All right? And then the last thing I'm going to do, I need that derivative, the derivative at that point. So it's going to be f prime of pi over 6 equals negative sine squared pi over 6 plus cosine squared pi over 6. Now, remember we just said the sine of pi over 6 is 1/2. So it's going to be negative 1/2 squared, like that. And we said the cosine of pi over 6 is root 3 over 2. So that's going to be root 3 over 2 squared. All right, and so from there it's just arithmetic. So negative 1/2 squared is negative 1/4. Root 3 over 2 squared is going to be 3/4. Right, so root 3 squared is 3, 2 squared is 4. And so negative 1/4 plus 3/4 is positive 2/4, or just 1/2, which works out kind of nice. Okay, so remember we have those three things for every single one where you need a equation of a tangent line. We have x, which we can also call a, that's pi over 6. We have our y value, which we can also call f of a, and that's root 3 over 4. And we have our derivative at that point, which we can call f prime a, and that's 1/2. Okay, so now we'll plug all that in. And so we'll do y minus root 3 over 4, that's f of a, equals 1/2 times x minus pi over 6. I would take that, that's the equation of the tangent line. Or what you can do is just multiply this out. So 1/2 x minus pi over 12, and then you can add the root 3 over 4 to the other side, equals y, and I would also take that. That's a little nicer looking, but it doesn't really matter. And again, what you can do to check is we're going to just graph f of x equals sine x cosine x. So let me just do that here for you. Okay, so there's y equals sine x cosine x, and I already forgot the equation, so let's pull that up. Here we go. So it's a little tricky to type this in, but not too bad. So y equals 1/2 times x minus pi over 12 plus square root 3 divided by 4. And that takes some practice, but you'll get it with time. And did I make a mistake here? What did I do? Oh no, it's good. So here's pi over 6 right here, and you can see that the line is tangent right there. To check and make sure you know where it is, you can do x equals pi over 6, and that'll put a vertical line here just to confirm that you have the right spot. But you don't really need that. So you can see it's tangent, so that means your answer is probably good. Let's say you made an error, right? And you accidentally thought the derivative was 1/4. Or let's say you accidentally thought that the y value was √3/2. So let's just say we have a mistake. Do you see how it's very clearly not the tangent line at pi/6? So that would be a hint that you didn't get it. Whereas here you can very clearly see that it is tangent to the original function. So that's a clue that you got it. You can also use ender, or not ender, but you can use the f prime x function to find the derivative as well, or to confirm your derivative in Desmos. Any questions there? Okay, so I know that's a lot of arithmetic, and you got to know a lot about the derivative. You got to plug in your values and everything. This is pretty standard for like a multiple choice question. You would see these on the AP test, and you'd get about 3 to 3.5 minutes to do this. So that's where you got to be kind of snappy about knowing your trig values. You don't really have time to reference them for each question. Any other ones? Okay. So I'll take a look at those as soon as I can. Kind of a busy week for me, but I won't give you another quiz until you get this quiz back. So I'm sure we can feel comfortable with that arrangement. All right, so let's talk about parametrics. We'll come back to the polar stuff. I just wanted to make sure those graphs were ready for us. Parametrics and their derivatives. And we're going to spend no more than 10 minutes on this because we already did that lesson on Friday. Okay, so remember that parametric equations are defined in terms of t. So we have x and y defined in terms of t. So we might have something like x of t equals 2t plus 1, and y of t equals sine t. Okay? And so you can think of t as time, and x and y are still x and y, right? So instead of having y as a function of x, you have x as a function of t, y as a function of t, and t is called the parameter. Okay? Now, even if you don't understand all that, you can still pretty easily find the derivatives here. So you can basically just pretend that, and you don't have to pretend anything, x is your dependent variable and t is your independent variable. Y is your dependent variable and t is your independent variable. So I can write that x prime t is 2, right? That's just a power rule. And I can write y prime t equals cosine t. Okay? Now, another way to express this, as we've seen before, is that we can call it y prime, or we can call it dy dx, which means the rate of change of y versus the rate of change of x. So we saw that with f of x, right? So if we have f of x and we take the derivative, we get f prime x, which we can also call dy dx, which means the rate of change of y relative to x. Okay? Now here, we don't have the rate of change of y and x, we have the rate of change of x versus t, so we can call this dx dt equals 2, and the other one we can call dy dt equals cosine t. So I didn't actually take any derivative there, I'm just showing that there's two ways of writing this, right? we'll call this 2 notations. So it's the same thing. How does x change when t changes? How does y change when t changes? Okay? So that part's pretty easy. The part that is a little bit tricky here is finding dy dx. Okay, so dy dx is the rate of change of y as x changes. Okay, and so the reason that that's tricky is because we only have equations that connect x and t, and we have equations that connect y and t. But what we want in terms of dy dx is some expression that connects y and x. Okay, and the formula for that is dy dx is equal to dy dt divided by dx dt. Or if you prefer the other way of looking at it, you could say that it is, well, I don't want to use the prime notation. The problem with the prime notation is that it's harder to connect what variables it is. So what I could do is say f prime x is equal to y prime t divided by x prime t. I'm not sure that's actually helpful in terms of understanding it, but it could be if you prefer that notation. The reason that I don't think it's helpful is because f doesn't mean anything, right? F is just some function that we name abstractly, so you can't see the variables as easily. Whereas with dy dx, you know that it's the derivative of y with respect to x, and that's equal to dy dt over dx dt. So if I wanted to calculate that, in this case, it would be cosine t over 2. And that's it, okay? So even if you don't have a totally firm grasp on what all this means and what's up with this parameter stuff and why can't we just do x versus y, this is confusing, whatever, you don't have to really worry about all that. All you really need to be able to know is this equation and to be able to take those derivatives and then divide them, okay? So let me start your homework off. So we're going to do 42, okay? So 42 gives you x equals sine of 2 pi t and y equals cosine of 2 pi t. I think we actually did this one already. So what I'm going to do here is change the t value slightly just to make this a different problem. And we're going to make t equals pi over 3. Okay? No, that's not good. Let's do t equals pi over 12. Yeah, that's good. And so the instruction here is going to be to find, let's start by finding, we'll call this A, find dy dx, and B is going to be find the equation of the tangent line. When t equals pi over 12. Okay, so again, you want to kind of think of t like time, and you can figure out what x is based on how much time has passed, and you can figure out what y is based on how much time has passed, and then we can graph that, and then once we graph it, it's basically the same as any other equation. Okay, so how do we find dy dx? Well, first we're going to find dy dt. So what's the rate of change of y with respect to t? So we just take a derivative. It's going to be negative sine 2 pi t, and then we got to do a chain rule on that, so times 2 pi. Next thing we're going to do is find dx dt. So we're going to do dx dt equals, and this time we're looking at x versus t. And that's going to be cosine of 2 pi t times 2 pi. So far all I've done is just taken a couple derivatives based on techniques we've already covered. Okay? Now here's the new thing, right? dy dx is going to be dy dt over dx dt, which we just figured out. dy dt is negative sine 2 pi t times 2 pi. dx dt is cosine of 2 pi t times 2 pi. And we can cross out the 2 pi's. And this is going to be negative tangent of 2 pi t. Or if you want, you can just leave the sine and cosines alone. Doesn't really matter. But I'm going to simplify it. So that's dy dx in terms of t. So this is actually telling us the rate of change of y versus x given what t is. So there's actually 3 variables here, which makes this a little confusing. But this is the only situation that you'll see in this class where there's 3 variables. If you end up going on to calculus 3, then that whole class is about how to do calculus with 3 variables. Okay, but I don't actually just want dy dx. What I want to do is find dy dx when t equals pi over 12, and that's the notation we can use for that. So what I'm going to do is I'm just going to plug that in. Or did we say pi over 12? Yeah. And this is then going to be negative tangent of pi squared over 6. Okay, so this doesn't come out clean. So I'm going to have to go to my calculator. So I'm just going to type in negative tangent of pi squared divided by 6. And this is going to be, I'm going to round it. It's going to be about 13.5. Okay? So that is the rate of change with respect of y with respect to x when t equals pi over 12. So those numbers did not come out nice, but sometimes they'll do that to you on the AP test where it seems like it's going to come out as a nice trig function, but actually it doesn't. Okay, so that's part A. Any questions on part A? All right, let me give you a minute so we're all caught up here. Okay, so remember that for the equation of a tangent line, what you need is an x value, a y value, and you need a slope, right? And we're going to do all of these when t equals pi over 12, okay? Now we just figured out that slope. So the slope when t equals pi over 12 is going to be 13.5. So how do we find the x value and the y value? Well, those are defined at the beginning of the question. So we're going to grab those. So x is equal to sine of 2 pi t, and y is equal to cosine of 2 pi t. So this is again going to require a calculator. So it's going to be sine of 2 pi times pi over 12. And it's going to be cosine, y is going to be cosine of 2 pi times pi over 12. So I'm going to put those in my calculator. You don't even have to simplify it first, you can just type it right in your calculator. And for this one you get 0.997. And for the other one, for the cosine, it's probably going to be close to 0. We'll see. We're going to get negative 0.074. We'll keep it consistent. Okay? So you have your x value, you have your y value, and you have your slope. Here's x, here's y, and remember we said that the slope is 13.5. And so from there we can just use point slope form. So y minus a negative 0.074 equals 13.5 x minus 0.997. And that's the equation of the tangent line. You could multiply this out. For the sake of time, I'm not going to do that. I want to make sure we hit everything. But that is the equation of the tangent line. So again, every tangent line in this class is going to be an x value, a y value, and a slope. The only difference here is that to find the x value, instead of it being given, you have to figure it out based on what t is. To find the y value, you have to figure it out based on what t is. And then the slope is going to be dy dx, which requires us to use this formula that we identified earlier, dy dt divided by dx dt. All right. So we'll come back to this. We're going to come back to everything before the AP test. Chances are this is going to fall out of your brain by April, which is fine. I mean, the main thing is that we build a foundation now, and then we'll get you ready for the AP test with a few weeks of review. Okay, so let's go to the next thing. Next thing is polar equations. So the thing about polar equations is that you don't really need to know them yet. We're going to come back to it at the end of the year. So I want you to kind of fuzzy know what they are. That's what my old engineering teacher used to say. Just fuzzy know it, meaning like, you kind of get it, but maybe you're not an expert. That's fine. Okay. So polar equations are kind of neat because they're not graphed on an xy plane exactly. So usually what we're used to is having x as our independent variable and y as our dependent variable. So we would call this a Cartesian equation. And we would say like f of x is equal to y, right? So to figure out what the y value is, we plug in x. All right, and just above we covered the parametric equations where we have y is a function of t and x is a function of t. For polar equations, we're going to say that r is a function of theta, okay? And r is a radius, and theta is an angle, okay? So polar equations are going to be for curvy, circular-looking things because we're interested in angles and radiuses. And so in terms of how those are defined, let's say we have a single point here. We're not going to get into this in a whole ton of detail. I just want to make some room for this. Okay, so in terms of how this point is defined, in Cartesian coordinates, we would give that point a coordinate based on its x value, and we would give this thing a coordinate based on its y value, right? In polar equations, we give this thing a coordinate based on its r value, which is how far is it from 0, 0, the radius. So you can think of it like well, that's basically it. It's the r value is how far is it from 0, 0. And then we also want to know the angle theta. Okay, so this point here is defined by r theta, the radius and the angle. And then you have a whole collection of points that are defined based on some equation. So now you've been seeing this little graph popping up here and there. Here's some examples of polar equations. So these things are kind of swirly whirlies, I guess you could say. So you have examples of how these things are defined. A circle can be defined by r equals some coefficient times sine of theta. And then the rest of these are just kind of extensions of that, like different graphs that you can produce. You don't really need to know any of these. Okay, I'm just showing you some examples of what you can do with polar equations. And what you should notice here is that none of these are functions in the traditional sense, right? When we talk about functions, we're talking about things that pass the vertical line test, and none of these pass the vertical line test. But because of the way we define them, we can do calculus on them even though they're not functions in terms of x and y. Okay? Now, you're probably asking yourself, like, whoa, that's a lot. What do I actually have to be able to do? And it is way simpler than you might think. So let's scroll down here. So we're going to call this polar derivatives. So you'll be given an equation, r as a function of theta. So an example could be r equals sine theta. Or let's call it, we'll call it 2 sine theta. Okay? And you'll get a question that says find dr d theta. Okay? You're literally just going to treat r and theta like x and y. So dr d theta, in this case, is 2 times the cosine of theta. That's it. Again, when you get to Calc 3, you're going to look at this, if you get to Calc 3, which I'm sure all of you could if you wanted to. Then you'll look at what this means in more detail and why it's useful, et cetera, et cetera. For now, you just need to know that polar equations are a different way of looking at graphs based on radius and angles. And you have to know how to take a basic derivative, okay? Now, one other thing you should be able to do is if I ask you to take dr d theta when theta equals, let's say, pi over 3, you just plug in pi over 3. Cosine of pi over 3 is 1/2, so it's 1. And that's basically it. It's very unlikely that you would be asked to do anything fancier than that. They're just going to ask you to do one derivative. So I gave you 4 of these for practice for tonight, and we're not going to do a classwork for the sake of time. you don't have to graph anything. You don't really have to worry about, the swirly whirly stuff or the definition that we covered. You're just going to find drd theta given an equation in terms of r. Some of these are going to be a little bit tricky. I can make a homework video if you need it, but I think you guys can probably handle it. It's all just chain rules and product rules and power rules and stuff like that. Okay, so let's go to 3.7. And we're just going to preview this. I just want to get the idea in your head, and then we will follow up on Friday because it's a H day, so I don't have you guys tomorrow. Okay, so this thing is called implicit differentiation. Okay, so first what we need to do is understand what an implicitly defined function is. Okay, so let's just address that. I think we briefly talked about this in chapter 1. I'm pretty sure we did. So an implicitly defined function is a function that has x's and y's in it. So we're actually going to look at the unit circle. Okay. And so you can graph this, and if you graph it in, let's do it in Desmos so that my sketchy graphs don't get in the way of your understanding of it. So this is going to be x squared plus y squared equals 1, so there's your unit circle. Okay, now in the traditional sense, this thing is not a function, right? It fails the vertical line test. But there's two functions that are implicitly defined, meaning that they're hidden inside of here, okay? And those two functions are going to be, we can find them by solving for y. So I subtract x squared, and then I get y equals plus or minus 1 minus x squared inside of square root. And I can show that in Desmos. So let me blink this one off. And we're going to call this y equals square root 1 minus x squared. And that's a function. And then we can say y equals negative square root 1 minus x squared. Oops. Not to the 12th, x squared, and that's a function too. So we would say that these two functions are implicitly defined by x squared plus y squared equals 1. Now you don't really need the details of that. This is awkward here. What you need to be able to do is just recognize that if you get an expression with powers of x and powers of y, that you're going to use the technique that we're going to discuss now, okay? Any questions so far? Okay. So here's an example, and then I'll have you practice one, okay? Let's say we start with y squared equals x, okay? And this thing, a graph of this looks like this. Okay, that's x equals y squared. So it's not a function, but implicitly defined inside of it is square root of x and negative square root of x if you solve for y, but you don't have to for this. All right. So what we're going to do here is we're going to take the derivative of the left side and we're going to take the derivative of the right side. Okay, so what we'll do is on the right side, we're going to take the derivative of x, and that's 1, right? That part's easy. The left side is where it's a little different, okay? So we're going to do a power rule on y, okay? So that's going to be 2y to the first power. Actually, let's not call it to the first power because that looks like y prime. So that's just 2y, all right? Now the chain rule tells us that we have to also multiply by what's inside. So what is the derivative of y? We call that dy dx. So this is going to be 2y times dy dx. Okay, so I know that looks a little weird. Just remember that the derivative of y is dy dx. So another way to think of this is we have y squared, right? So we do a power rule on it, 2y, and then we have to take the derivative of what's inside, which is dy dx. So that's how we got that, okay? So I'm just going to put that off to the side. So now to find the derivative, we're going to just solve for dy dx. So it's dy dx equals 1 divided by 2y. Okay, now that's pretty strange, right? It's strange because we're used to seeing dy dx in terms of x. This time we have it in terms of y. But that's how these work, okay? That's how we solve implicitly defined functions when we take the derivative. Okay, so let's do that same thing with the unit circle. So we're going to make this a classwork. And this is classwork 1. So we're going to find dy dx for x squared plus y squared equals 1. So what's the derivative of x squared? It's just 2x, right? That doesn't change. What's the derivative of y squared? Well, we actually just showed that. It's going to be 2y times dy dx. So basically, like the hint here is anytime you do a derivative involving y, you have to multiply by dy dx at the end. Derivative of 1 is 0. Okay, so we have an expression now that includes dy dx, but now we have to solve for it. So I'm going to subtract the 2x from both sides. Then I'm going to divide by 2y. And then I can cancel the 2's, and I get negative x over y. So what that means is, if I want to know the derivative for an implicitly defined function, I need an x value and a y value. Now let's say I specified, for example, let's say that we're going to find it at, well, we'll do that on the next one. All right, so let's do classwork 2. Unless anybody has a question, you guys with me? Okay. So this time, I'm going to give you a point. Okay, so this one's going to be find the slope of x squared plus y squared equals 25 at 3, -4. So essentially what I'm asking you to do here is, here's a circle, has r equals 5, right? Radius 5, that's x squared plus y squared equals r squared. We did that way back in chapter 1. Okay, 3, -4 is going to be roughly here, which I'll do in pink. And so the slope, the instantaneous slope, will be the slope of the tangent line here. So that's what I'm asking you to find. And the reason that you're given an x value and a y value is because technically at x equals 3, there's 2 possible y values, right? It could be the point above or it could be the point below. So you need both to be able to do this problem, both x and y. So I'm going to take the derivative of this thing, and it's going to turn out to be exactly the same. So x squared, 2x, nothing fancy. Y squared is going to be 2y times dy dx. Derivative of 25 is 0. Now, if you're paying close attention, like I just mentioned, this is the exact same derivative, which is kind of cool. That means that the slope of a circle exists independently of the size of the circle. It's kind of cool. So I'm going to solve, and I get dy dx equals -x over y. And the reason I'm doing it so quickly is because we just solved it, right? So now, here's the new piece. I'm just going to plug in those numbers, right? So -x, which is 3, over y, which is -4, which is 3/4. Now, let's say you wanted the tangent line here. You don't have to write this down. But remember, the tangent line is always just this thing. It doesn't matter what the application is, the tangent line is always defined by that. So we have x is 3, y is -4, and our slope is 3/4. Now, we defined the slope a different way than usual, but it's still, we know the slope. It's, it's 3/4, right? So then we just plug that in. And you could simplify more from there, but I'm not going to. Okay, so we're going to do number 1 from your homework so that you're off to a good start here, and then that'll be it, okay? So this is page 162, number 1, and you're going to find dy dx for x squared y plus xy squared equals 6. So this is 2 product rules, okay? So you're going to end up with kind of an algebraic mess at the end. the first product rule is going to be x squared times the derivative of y, which is dy dx, plus y times the derivative of x squared, which is 2x. So that's just a product rule, keeping in mind that the derivative of y is dy dx. Okay? That's the first purple part. Then to that, we're going to do x times 2y dy dx, that's the derivative of y squared, plus y squared times 1. And that's going to be equal to 0. Now, the rest of this is solving for dy dx, okay? And what you need to do to solve this for dy dx is to group the terms involving dy dx together on one side. So I'm going to subtract this thing and this thing to the other side of the equation. Negative y squared minus 2xy. So I just subtracted the orange things. Then I'm going to factor dy dx out. And then I'm going to divide by the expression in the parentheses on both sides. And that is it. So yes, I know that's tricky. We're going to spend another day on it on Friday. I'll take your questions. If you need a homework video, let me know. I can work on that for you. And that's it, okay? So hang on if you have questions. Otherwise, I will see you next time, okay? See you guys later.